Oh, it's time for Le Chatelier. That's correct. Topic 9.06, finishing off this unit with Le Chatelier's Principle, making equilibrium serve your evil needs. To understand this, you have to recall the factors that affect the rate of the reaction, because we're going to tweak with them. Remember we said that systems at equilibrium stay that way as long as it's in a closed system? Well, we're going to open that sucker up and mess with it. Oh, yeah, we are. So, remember, equilibrium is when the rate of a forward change equals the rate of a reverse change. But if we change the rate of one of those more than the other, well, we're going to mess with our equilibrium. An equilibrium will always shift in a direction that reverses whatever you did to it. So temperature. Remember, if you increase the temperature, you'll increase reaction rate because you'll increase collisions. If you increase pressure, you'll increase reaction rate because you'll be squashing the molecules closer together so they'll hit each other more often. If you increase concentration, you'll be putting more particles in the same amount of space, so they have a greater chance of hitting each other, making the reaction go faster. Catalysts and inhibitors lower the activation energy or raise the activation energy, but they do so for both the forward and reverse changes equally. So catalysts and inhibitors will get you to equilibrium faster, but once you're at equilibrium, they won't have any impact on equilibrium at all. They'll make the forward and reverse reactions either faster or slower by exactly the same amount. And surface area doesn't affect equilibrium because solids are not impacted by equilibrium systems. Gases and solutions are. So, let's look at Le Chatelier's principle. If you take a system at equilibrium and subject it to a stress, which is defined as anything that disproportionately affects reaction rate of either the forward or reverse reaction. This can be in the form of changing the temperature, pressure if it's a gas, or concentration if it's a solution. The equilibrium will shift in a direction that reverses the stress, which will result in a changing concentration of both reactants and products until you reestablish equilibrium. So imagine you're sitting in front of a fire and you start to feel too hot. That's a stress. So you shift in a direction that reverses that stress. You're too hot, so you'll shift away from the fire so that you feel cooler. That's what I mean by stress and shift. It's cause and effect. The change in concentration will result in you completely reversing your stress. And that's what I want you to keep an eye on as we go through this. Equilibrium will shift away from whatever you add to use it up, and towards what you remove to make more of it. Again, reversing what you did. You'll make more of whatever you shift towards by using up what you shift away from. So let's look at some actual examples of this. Oh, and by the way, if there's more moles of gas, that means more pressure is being exerted. 2 moles of gas in the same amount of space is going to exert twice as much pressure as 1 mole of gas. Okay, so here we have the Haber process, a reaction that generates ammonia. Nitrogen and hydrogen undergo a synthesis reaction to produce ammonia, and heat is generated by the forward reaction. But at a certain point, this reaction can begin to reverse. Well, why is that? Well, the forward reaction is exothermic, which is favored. But you're taking 4 moles of gas and turning them into 2 moles of gas. That's going down in entropy. That's unfavored. And since one factor is favored and the other is unfavored, this reaction at some point will reverse, and we want to find out what happens at that point. The forward change will be exothermic, which means the reverse change would be endothermic. Okay. First stress. Let's inject some nitrogen gas into this system. This will result in an increase in collisions between nitrogen and hydrogen. This will speed up the forward reaction. If the forward reaction is made to move faster, the reaction will shift forward. This means that nitrogen and hydrogen will be used up faster than they can be reformed. So over time, the amount of nitrogen and hydrogen will decrease because they're getting used up faster than you can remake them. And since we're making ammonia faster than we can break it apart, the concentration of ammonia will increase. If you add ammonia, you'll have increased collisions between ammonia molecules, causing them to break apart faster than they form. Since ammonia will break apart faster than it forms, the reverse reaction speeds up. The equilibrium will be towards the left, to using up ammonia, which means that we're going to make nitrogen and hydrogen faster than we can combine them, which means their concentrations will increase. And since we're using up ammonia faster than we make it, its concentration will decrease. If we remove hydrogen, there will be fewer collisions between hydrogen and nitrogen. This will slow down the forward reaction, which means nitrogen and hydrogen will form ammonia slower than ammonia breaks down to form nitrogen and hydrogen. So the reaction will shift in reverse. Since nitrogen and hydrogen are breaking up slower than they can be formed, the concentrations of both increase. And since ammonia can now break down faster than it's formed, its concentration will decrease. If we remove ammonia, there'll be fewer collisions between ammonia. The reverse reaction will slow down. Since the forward reaction is now faster, nitrogen and hydrogen will break up faster than ammonia can break up, so the shift will be forward. Nitrogen and hydrogen will be used up faster, and ammonia will build up. So I want you to notice, whenever you add something, equilibrium will shift away from the side that what you added is on. You add a reactant, the equilibrium will shift towards the products. You add a product, the equilibrium will shift toward the reactant. And the resulting stress will use up whatever it is you added. So if you add N2, the result of the shift will be to bring N2 back down again. And if you add NH3, the result of the shift will be to bring NH3 back down again. If you remove H2, the equilibrium will shift in a way that brings H2 back up. And if you remove NH3, the equilibrium will shift in a way that brings NH3 back up. If we increase temperature, it's going to be too hot. We can move away from the fire, but a bottled up reaction can't. But what it can do is shift in a direction that brings the temperature down. The forward change is exothermic, which releases heat. So if you want to absorb excess heat, you want to shift in the endothermic direction. As a result, not only will you use up the excess heat, you'll also use up ammonia to make more N2 and H2. And if you decrease temperature, the shift will be towards the exothermic direction, towards the products, which means we will use up N2 and H2 faster than we can break down the NH3. So once again, equilibrium shifts away from what you add. You add heat, equilibrium shifts away from heat. You remove heat, equilibrium shifts towards heat. The concentration of whatever you shift away from decreases, whatever you shift towards increases. Finally, pressure. If we increase pressure, equilibrium will shift in the direction that has less pressure. The left side of this reaction contains 4 moles of gas. The right side contains 2 moles of gas. If we increase pressure, the only way to bring pressure back down is to shift in a direction that produces less molecules. The right side has fewer molecules. And since we're shifting to the right, the stuff on the left will decrease and the stuff on the right will increase. So we're going to go from having 4 moles of gas to only 2 moles of gas if this went all the way. The opposite is true. If you decrease pressure, you're going to shift toward the side that has more moles of gas, causing that side to increase, bringing the pressure back up again, and the other side to decrease. So whatever we add, we shift away from. Whatever we remove, we shift towards. Whatever we shift away from will result in a decrease. Whatever we shift towards will result in an increase across the board. Let's apply that to this other solution. Hydrogen plus chlorine forms hydrogen chloride. If we add H2, the equilibrium will shift away from H2, making not only H2 but also Cl2 decrease. We'll make HCl faster than we break it apart, so its concentration will increase. Whatever we shift away from decreases, whatever we shift towards increases. If we add HCl, the equilibrium will shift away from HCl, bringing its concentration down and the stuff on the other side up. HCl's concentration will decrease. If you remove Cl2, the equilibrium will shift towards Cl2 to make more of it by using up HCl. If you remove HCl, the equilibrium will shift forward, using up H2 and Cl2 so you can bring the amount of HCl back up again. If you increase the temperature, the equilibrium will shift in the endothermic direction away from heat, bringing the reactants up and the products down. If you decrease temperature, the reaction will shift in the exothermic direction, bringing the reactants down and the products up. If you increase the pressure, there's 1 mole of hydrogen and 1 mole of chlorine for a total of 2 moles of gas on the left side. My cat just deactivated this PowerPoint with his tail. So let me get back to where we were. Thanks, Jack. I appreciate that very much. He's a very sweet cat. I'm going to remove the keyboard from the desk. Because there's the same amount of gas on both sides of this reaction, the net change will be no change at all. There's nowhere for this equilibrium to shift to relieve the excess pressure. So all the concentrations will remain the same. And the same is true if we decrease the pressure. There's nowhere for the equilibrium to shift, so the equilibrium will not shift. Equilibrium can only shift if it can, and if it can't, then it won't. Now for a solution equilibrium. If we add potassium ions, now you're not going to find a bottle of potassium ions sitting in your chemical storeroom, but you can find bottles filled with compounds that contain potassium ions, like potassium chloride or potassium nitrate. So if you add any compound that has a common ion to your equilibrium, that will have the effect of increasing the concentration of that ion. Since you're adding a product, the shift will be towards reactants. We'll make more precipitate while using up our ions. If we add potassium chlorate, well, since we're at equilibrium, this is a saturated solution. That means no more can dissolve, which means there's no shift at all. If your solution is at equilibrium, it's saturated. No more ions can go into solution. They can only come out of solution. If we remove potassium, then now you're taking something out of solution. This will allow more ions to dissolve. If you remove chlorate, the exact same thing is true. If you increase the temperature, the equilibrium will shift in the endothermic direction, which is forward. You'll use up some of your solid and you'll form more ions. If you decrease the temperature, the exact opposite will be true. So this solute will be more soluble at higher temperatures and less soluble at lower temperatures. And of course, since there are no gases here, it doesn't matter what you do with pressure, you'll have no effect at all on your solution. So how can you make equilibrium do what you want it to do? So what direction do I have to make the equilibrium shift to get the results I need? So this time we're going to work backwards. Let's say we have this system at equilibrium. What can we do to force the equilibrium to make more B? Well, if you want to make more reactant, You're going to have to find a way to make the equilibrium shift towards the reactant side. What are some things you can do? Well, we can make it shift towards the reactant side by adding a product. This will force the equilibrium towards the reactant side. We can remove a reactant. That will make the reaction move towards the reactant side. We can even go in there and remove some of what we're trying to make more of, and that will shift the equilibrium towards that side to make more of it. We can increase the temperature in this case because temperature is on the right side. Increasing temperature will push it to the left side. And because we have 3 moles of gas on the left and 2 on the right, in this case, decreasing pressure will shift to the side that has more gas. So you can reverse the process of Le Chatelier's principle to make predictions about what you can do to get the equilibrium to do what you want it to do. If we wanted to make more C, we could add A, add B, remove C, or remove heat. Or we could increase the pressure, shifting equilibrium to the side with less gas. That is all there is for this unit. It's been a long unit. It's been a little weird. I know it's a little difficult. You may have had to go back and watch these videos multiple times. That's fine. That's what they're here for. It's kind of like a catalyst or an inhibitor. Once you finish using them, they're still going to be here in case you need to use them again. Next unit we're going to do will be on solutions. Saturation, unsaturation, molarity, colligative properties. So join me for that, and I'll see you then. Actually, I won't see you, and technically you won't see me. You'll hear me, but you won't see me because I don't have a camera on right now. Anyway, bye.